Welcome. This is Module 6 of a course called Coding for Crosswords. For information on the full course, please see the links below. In this module, we will introduce the basic notions of object-oriented programming. We're still in COVID. I've got my COVID hair, and now we have wildfires as well. So it's a good time to sit back and learn how to program. Let's start by looking at where we ended up from the previous module. Let's go to the source window. And let's bring up that code, and it's here. So first we have these include files. An IOStream is the one that will allow us to output characters to the screen. That's covered in Module 3. String is a basic class that allows us to form these long strings of characters like this that we use, and that was discussed in Module 4. And then vector we introduced just in the last Module 5, as well as assert. And those let us manipulate sets of things together, sets of strings together. And then the assert macro lets us check that certain things are true about the data that we've assembled. So let's look a little further down and see what we're doing then. We've made a vector of strings, which we call grid. And we're pushing back to that grid all these strings. Let's review. The problem we're trying to solve in this course is to take this crossword puzzle and have the computer program read a library in and try to find the right words or many combinations of words that will construct a crossword puzzle that will be legal, that will have legal words, and that then you could use to publish this crossword puzzle. So there are three things that we have done here with this vector of strings called grid. The first part here is to load the grid with some data. The second part is to check the grid for some attributes that we want to be true, such as that the length of every string in the grid should be the same as every other string. And then finally, we print some information about the grid. We can print how many rows it has, how many columns it has. We can actually print the actual grid itself. So those are three types of functions that are being performed on this grid. And in this module, what we want to do is get you to think about objects. Object-oriented programming is the basis of all modern programming languages. And in the last lecture I mentioned there's this spidey sense you get when you see code like this that's sort of scattered in the main function. We don't like to see code scattered like that. We'd rather group it into something, into an object. And before we do that, there's one first step, and this has to do with the way that we think about objects. Now, I've called this vector of strings grid. Now, in fact, what I want to do is introduce really a higher level thing called grid. Let's make a variable called grid that's of type capital G grid. We're going to define what this thing is. And we'd like that to be a higher level concept of the entire grid. Now, the grid, yes, it does contain some strings like we've shown there, but it also might contain other information. And it could be anything that has to do with that grid, like maybe when we loaded it, or is it valid, or any other attribute about that grid that we want to collect with the data on the grid. So the first task, and this is the first challenge for you, is we're going to change the name here. We're not going to call the vector of strings in the grid also grid. We're going to call that something different, and we're going to call it lines. Okay, so we change that here. What I'd like you to do is follow this change through in your own code and get that to compile so that we can all start with the same code. So go do that now. Okay, welcome back. Let's see if we can finish this change together. What I was asking you to do was to change these grids. Since we're changing the name of the grid, we're changing the meaning of grid to be a higher level thing, and we want just the lines in the grid to be called lines. We're going to change every one of these grid to just lines, right? So now We'll see if that compiles. We go to the execution window and we type in G++ minus O, the output file I just call A, and then A.C. If you haven't seen this before, go to the previous lectures. For example, module 2 will show you how to get this going in different environments under Windows or Chrome browser or Linux. So here we go, we run this, and it's going to complain that it doesn't know what grid is, right? We haven't told it yet what a grid is. So let's hold off on that. Let's just comment that out. And this is a common technique you can do when you're sort of prototyping code. You can type some of it in, kind of get it partially right, and then comment it out, and then just see if you can compile the other part. So here we go. So that compiles, and let's just run it and see what it does. And it's just printing down here. It's printing these rows and columns that we set at the bottom. So now, here comes the important part. We're going to define the grid object. And in C++, the way you do that is you say struct. It's a structured data. That's kind of an older name for it. Class is also a newer keyword you can use. But we're going to just keep it simple now and use struct. And we're going to define it as grid. So that's the name of our new structured data object. And it has the guts of it, again, just like other things. You put everything inside this new grid you're going to put into this parenthesis thing here. And what we're going to do is take these 7 lines here and we're going to move them up into here. Somehow we want this load function to get up into the grid class. So we're going to move them up there, and we're going to, down here, we're going to say grid, call that whole thing load. Okay, so it's a new function we're going to define called load. And we'll go up here and have to define it. We're going to say load. And again, we're going to put everything that we want to have inside the load function inside a new set of parentheses. So here's this new thing called load. It's a function. And we call it here. So there's still a few things wrong with this, but I want to get the general idea across that we're trying to move some of this function that was in the main loose, and we're going to pack it into grid. We're going to keep doing this. Now, there's some problems with this. I want you to go ahead and run this. So this is another challenge. Go ahead and run this code, and let's see if you can help, see if you can figure out how to get through the compile errors. And if you can't, we'll do it together in a minute. Okay, welcome back. Let's go through some of that together and see what happens. Let's go to the compile window, and let's try to compile that thing. Now, there's a number of problems here. The first is that this function, this is called a member function, load, here, where we defined it to be all the pushing back of the lines. That needs a type. Just like, remember how main down here, main had a type called int? Well, load needs a type. So here's what we can do as a first try. We can make it an int also. We can say, okay, load is going to be of type int. It's going to take no arguments. Remember in here, this thing is where you put the arguments that you pass to the function, and then this thing out front of it is the return value of the function. That's what the function returns. So these are the ins to the function, and these are the outs, or the one out. But it can be a complex data object also. But there's no inputs to this function right now. It's just load, and then it returns, let's say, an int. So let's see if that gets us out of at least one of the problems. So go back to the compile window, and let's see. Let me run that like this. So now, this is another just syntactical problem. This struct that's in between these parentheses, for kind of historical reasons, needs a semicolon at the end here. It's something that's not obvious, but that's just the way C++ is. So let's put that in, and that will help. So let's run that again. Okay, now this is a more fundamental problem. It's a scope problem, right? We've pushed this work of loading the lines with this data up here. We've pushed it into this other thing called grid. But from the point of view of grid, it doesn't know what lines is. It doesn't know what this lines variable is. Lines is way down here. Lines is still down in main. Now that's something that's kind of wrong, right? We don't want lines in main. We want just a grid in main. So let's fix this. Let's put grid back, and let's take this lines out, and let's actually move it up and put it in the grid. So this is kind of a neat idea. Not only do you have functions in this thing called grid, you also can have data. So that's the whole idea of object-oriented programming, is that you have complex data packaged in this object called grid, and then you have functions that can work on that data. So now we have the grid object that holds both the data and the functions that work on it, at least one function that works on it. So let's see how we do now. Let's go back and try to compile this and just see where we are. And what we get here is that we've defined load, this function here, as an int return, but it's not returning anything. Now main, we did the same thing for main. If you noticed, we kind of got away with it. There's sort of a glitch where, or sort of a freebie, where the compiler will let you get away with declaring main as an int, but not actually returning something. To be strict, we really should have said return 0 or some number here. It doesn't really matter. That gets interpreted by the operating system. You know, Windows will handle this a little differently than Linux, but 0 is fine to return. What we really need to do in here is put in a return here of 0. Let's just go back to the compile window and see how that looks. And let's see if we can get this to compile. Now, there's a different kind of error. We've moved some of the functionality here, the lines, up to the grid object, but we're still down here in the main function. We still have this other stuff where we're still calling lines. Okay, so we're going to get to that, but just for now, to get this to compile, let's get the scope right. It's no longer lines that we're accessing. It's actually going to be grid dot lines. It's like the lines inside the grid object. So just like we can call a function like size on lines, we can also say, hey, lines is part of the grid object. So all the lines, we can say grid dot lines. Okay. So let's just get this to compile, and then we'll do some more work to fix the code up. But here we go back to the compile window. Okay, that compiles, and let's run it, and that gives us the same output. Okay, now, and this is the challenge, let's fix up this use of the grid lines here in the source window. Let's get rid of all those. So what I want you to do is write 2 more routines, just like load. We want another one called grid check, and we want one called grid print. How about those 2? Okay, and so take all this code down here. All of this code should be, well, not that one. All this code, pack this into these 2 new functions inside the grid object and see if you can get that to compile and give the same rows equals 7, cols equals 7 output. Okay, go. Okay, welcome back. Let's see how you did. Now this one was hard, so don't be disappointed if you didn't get this. This may take a little figuring out, and we'll do it together now, okay? So first we want to take this check function. So these 5 lines here are really involved with checking if the grid is valid, right? So we're going to move those up to a new function called check. And let's call it like this. Okay, so everything within these brackets here has to do with this checking function. We're getting the number of rows, which is the line size, and then we're getting the number of columns, which is the first line's number of characters. So the line size is the number of lines, which is the height of the thing, which is the rows, and then the number of characters in the first line is the number of columns. Okay, so, and there's one more problem here. Do you see it? This is the sort of a mini challenge. Now that we're inside the grid, we've moved this code from the main up into the grid. We don't have to put this anymore. In fact, we must not put that because it won't know what grid is down here. We're inside the grid already, so we just need to look at the lines itself. So this cleans up that code and makes it look better because now the grid is accessing its own variable that's in its own scope called lines. Let's go back here and see what else we have to do. This last stuff we want to put into a print function, right? So let's go back up and let's add one more function, print. All right, so the print is just the stuff in here, and we're going to put that out. And now we're printing the number of rows, and we're printing the number of columns. And the rows was found up here, and is printed here, and the columns was found up here and is printed here. So this is the next challenge for you, is this going to work? And do you see what can go wrong with the code we've written right here? Do you see something that's going to cause a problem when you compile this? It means to do the right thing, but the compiler is going to be confused. Try to figure out why. Try to figure out why before you try it yourself and then see if you're right. Okay, go do that challenge. Okay, welcome back. Well, you might have figured this out. Let's just do it and we'll do it together and we'll look at it. So here we go. We compile it. And now it says, look, line 26, which for me is here. It says rows was not declared here. See, this is the problem, is the rows is a local variable. Everything in C++ and in, I think, all programming languages has an idea of scope. So rows is a variable that exists right here inside this check routine only. A different routine can't see it. It doesn't know what that thing called rows is. It hasn't been set here. So this is an interesting design problem for the class called grid. In general, how would you ask a grid how many rows it has? You'd like to be able to ask the grid what its size is. So what we want is a little helper function. We're going to make a new function called rows, right? And we are going to put in that function the thing that's up here. So we're going to put here, now we're going to say return, because we want rows to be a function that returns the size of the thing. And we're going to return not rows anymore. We're just going to return the number of lines in the thing. Now, you could call this rows at any time. And in fact, it may be 0 if the routine up here called load has not been called yet. So whenever you add routines like this that are utility routines that manipulate the grid or ask it a question, you have to remember they can be called at any time during the lifetime of the grid, before other routines might have been called. So when you write the code, you might have thought, oh, I'll always call rows after I do the load. But some other user or yourself later might make a grid and then call rows first. And it will return a 0 here, which isn't fatal for this case. But if you look at the columns case, let's do the same for columns. What are we going to return here? We want to return here, we want to return this thing. We want to return the size of the first line. Now, what if the grid has not been initialized? So this is going to be the next challenge. So this is a challenge. What error is this going to cause if you call calls on a grid that has not been loaded yet? So let's back into this a little bit first. Let's clean up the code so it'll compile first of all. So this rows here, we don't even actually use it in check, so we can just get rid of it. And this columns here, we do use. But this is interesting. We actually don't need this whole line anymore. This whole line can go. And what we can do is just replace that with a call here. So let's just walk through that one a little bit more carefully. I used to be computing in the check routine. I used to be computing the number of columns by looking at the first line and how many characters it had in it. All I've done now is I put that piece of function, I've put it into this other thing called calls down here. So it's the same thing as being run. It's just being run as part of a function rather than inlining it in the check itself. And then the whole point of what we've done here is that we don't need to access these variables rows and calls here. We can access the functions now. So let's make sure this compiles, and then let's make sure we're on the same page, that everybody to understand what this is doing. So first of all, let's compile this. And here's just another error. So we did make this an int, so we need to return something. Let's return 0 again. It doesn't really have any meaning. We'll fix that in a little bit. And then another one is this one, also same thing. Right. So let's get this to compile. All right. So let's recap a little bit, and then I'll go back to that challenge. Let's go back to the source window. Let's start back at the main. Look how simple that is. And this is great. This is the kind of code we want. We want really clean interfaces to things. So when you have an abstraction like a grid, the grid means it's a grid of crossword puzzle letters, right? And they could be in different state. They could be blocks, those black squares. They could be blanks, which means that there's no letter in there yet, or they could be the letters A through Z. That's what a grid is. It's a set of all those characters in a 2x2 grid arranged in rows and columns. So we're going to load the grid, we're going to check the grid, we're going to print the grid. That's a really clean interface. So that looks good from an object-oriented design perspective. You want to aspire to this type of a design as much as you can. Now, it's not always possible to be this clean because there's all kinds of real-world things that creep in where you want to feed extra information at different times to the object and so forth. But for now, this is a very clean interface. So this part I'm very happy with. Now up here, this is getting a little bit more complicated, right? This is getting a little harder to understand. Let's maybe group this. Just for formatting purposes, this is often done. These little helper routines like this, the rows and columns, often can go kind of somewhere easy, like maybe up high like this. Okay, so within a grid structure, you might have a number of these kind of quick little helper routines, like, hey, ask me how big I am, what's my name? So let's put those up high. And they're just single lines, and those are often inline like this. Usually you don't want to put, like if you were going to print something here, hello, if you had a print statement, you wouldn't want to inline it like that. That's usually not very good style to put two statements in one line, but if it's just the one line, it's not bad to have it like that. So then here's the load function, here's the check function, and here's the print function. And then there's the data of line. So even though it's starting to look a little bigger now, don't be intimidated by how much code there is because it's very well organized, right? We know there's a little helper routines, then there's the three main functions, then there's the actual data called lines, and then we use the thing. So even though we're growing now, we're 42 lines of code here. In your mind, I think it should be fairly straightforward to understand what that code is doing. So what was well, let's go back and check and make sure that this compiles again, just so we haven't messed anything up. Okay, so this compiles and runs. Now the challenge I wanted to ask you was, we've done something a little bit scary here in that we've let this routine columns do something here, which is it's accessing the first element of lines. Now what do you think would happen if you haven't called load yet? Let's try it. So what I want to do is let's hold off on these things. Check. Actually, we can let these go. Let's just take out the load. Let's forget to load the function, and let's see what happens when we just check to see if it's there. So the check will work because the lines will be empty, but let's see what happens with a print. So here's the challenge, finally, is run this code now with the load commented out. In fact, you could comment out the check too if you want. And let's see what happens there. Give that a try. And this is actually going to differ depending on your compile environment. But let's see what happens. Okay, welcome back. Now something bad should have happened. And do you see why? Because you never loaded anything into the grid. So what happens with lines? This variable lines here is empty, right? It has nothing in it. So when you call print now, look at what print does. Print tries to say, oh, how many rows are in the grid? And let's go look at what the rows does. The rows is up here. It just returns the size of the line. That's going to be 0. That's fine. And then it says how many columns are in the grid, and it calls this columns function. And that's where the problem is. Look at this. It tries to access the 0 element of lines. That's the first element of lines. But lines is empty, and that will cause a problem. In my environment here, Linux, this is what you get. It's called a core dump, which means that it tried to access something that did not exist. And you could go through and take the core file that it produces. That's from old-fashioned days of like the memory with the actual core memory. They dump the actual like little memory, like little rings that have the memory in them. But we don't need to do that much because we know what's going on in this small example. So let's add something to fix this. What's a good way to fix this? Well, I think the right way to think about this is that this function called calls that we've added up here is not a function that we can call at any time. It's a function that only can be called when the grid is full, or we could handle it. So we have to decide, do we restrict the interface that you can only call calls when the grid is full, has been loaded, or do we make the function calls robust against that case? And this type of design decision happens all the time, and you need to be very clear. There's no right answer. It's just when you design an object like a grid in this case, you have to publish as part of the interface what is the behavior of all your functions under different cases. And so let's try the first case first. If we wanted to say, call these only on loaded grid, right? That could be a note that we put as sort of a warning on these two functions. And then what we can do is we can say assert here lines, and can you think of a good way to do this? You could say size not equals 0, right? But a nice way to do this is to use this function called empty. It's the same thing. It's just, you could say we're going to assert that the lines is not empty, that we have some lines in there. So now if you call calls on an empty grid, a grid that has not been loaded with data yet, it should fire this assert, and that's a clean error. That's much better than a seg fault. So let's see how that works. Let's go down here and compile that. And there we go. There we get a clean assert. And in general, those are easy errors to look at because you can zip right in and see, oh, line 11. Oh, if somebody ran this code and saw this, they would see that assert. They would say, oh, wait, why did it not work? And they would scroll up here and they would say, oh, call these only on a loaded grid. In fact, you could even add a note here saying grid must be loaded, something like that. Then when someone, maybe yourself or somebody else, uses this code and it fails, they can see right away why it failed. Oh, I called this thing. I tried to ask it how big it was when I hadn't even loaded it. So that's one way to do it. Let's do a second way to do it, which is we can just handle that case. Let's eliminate this restriction and let's allow calls to be called anytime. But just like rows returns 0 when it's empty, let's say under the condition of, and this is a brand new statement we haven't introduced yet called an if statement, if lines is empty, okay, return 0, else return the size. So you see what this does is it protects the call against asking for the first line by checking to see that there is a first line available. So this is also a perfectly fine design pattern. And now when we run the program, what do you think is going to happen? Let's go find out. Remember, we're running this program under this condition here. Remember, if you look back to the source window, in this case, we've just for now commented out the load and the check just to see what happens if you take a grid that's completely empty and then you just try to print it, right? And that you could support that. I think it's a reasonable argument to say that that's something that you want to support because you should just have it behave in a nice way. And the nice way, let's check it out. The nice way for us right now is to say, yes, 0 rows, 0 columns, because you haven't put anything in it yet. Okay, so that was one item. Another thing that we can fix about this code is that you've noticed we've got these return statements in here, right? This return statement actually has some meaning. It's returning the value that rows is asking for, and this is returning the value that calls is asking for. These routines really don't have anything to return. There's no reason for them to return 0. So there's a special construct for that. Instead of saying you're returning int, you can say, I'm returning nothing. And in C++, that's called void. So it's saying, hey, look, these functions are not going to return anything. Now, what does that mean then also? You need to get rid of this return. Let's see what happens if you compile that without removing the return. It's going to say, hey, you're trying to return something, but you told me that the load and the check and the print functions are void returns, so they're not supposed to return anything. So let's get rid of these returns here. Okay, that cleans up the code and makes the function's signatures, these things are called the signatures of the functions, more accurately reflect what the function is really doing. In this case, it's loading some data and it's not returning anything. Now you might have wanted to return maybe a number that indicates, it could indicate the size of how many lines were loaded, or it could indicate a success or a fail of loading it if you were loading it from a file, for instance. So there's other ways you could put information in the return value, but for now we're going to leave that as void. So let's make sure that we've got back to something that will compile here. Let's put back the load and the check functions. And in fact, we can just get rid of this return too, because we don't really need it for the main. It's a bit lazy, but okay, we'll clear this. Right, and we're back to 7 and 7. There's another concept that I struggled whether to introduce it now or not, because you don't strictly need it, but it's really good design style to just learn it early and start to always use it. And that's a C++ notion called const. Okay, const is a very important and useful concept, which means it doesn't change the thing. So const can be used in a couple different contexts. One context it can be used is as a modifier to these functions. Let's go back here. Which of these functions modify the grid and which are just telling you things about it? So does rows modify the grid? No. It only tells you how big it is. So what we can do, this is the way it looks. You put a const attribute here. It's after the name of the function, after the input argument. So if you had any inputs, it'd be here. And then you put the const here. Okay. So we're going to also put the const on the columns because it doesn't modify the argument. Now what about load? Well, load is actually doing something here, but just for a game, we're going to put in const in here, and we're going to try to see what it complains about. How about check? Do you think check is a const function or not? Does it modify lines? It probably shouldn't, right? And then print shouldn't either. Those are all just functions that are read-only. You know, const means constant or read-only to the object. So here's a challenge. Try to compile this where we have const on the load function, which is changing, and see what error message you get. Okay, welcome back. Let's see how you did on that. Let's do it together. We compile it, and boy, it doesn't like that, does it? And this is an example of where the error messages from the STL library are really terrible. But if you go back up to the very start of this, you can see error passing const into the pushback function. So it's basically saying, look, the compiler is saying, you told me that this load function is const, but then you're trying to take lines and you're doing something non-const to it, because pushback itself is not const. So within a const function, everything you do to all the data objects inside this object have to also be const. So it kind of propagates. It's a requirement that you put at the top that requires everything else you do inside it to be const. But the whole reason it's useful is that conceptually, if you have a function that works on an object and you know that it should not be modifying the object, it's very useful for the compiler to tell you, hey, you call the function somewhere in there, anywhere in there, or you called a function which called another function, it passes it down, that was non-const. So that's like a sign of danger. Like, why are you even trying to call a function that could modify the object when you've said that this top level function like load, well, actually load does modify, but top level function like print, say, print does not modify the object. So that's why this const up here in the source window, we can take it out now, okay? And let's recompile that and just get back to where this runs. And we're back to having it run. Let's do one more mini challenge on this. Let's go back up and let's say that, suppose we had not declared rows and calls const. Do you think this would cause a problem? So this is a mini challenge. Just try to decide, try to think for yourself, would this cause a problem? When are rows and calls used in the code? And if they're non-const, where would that cause a problem? Try to guess what line number the compiler will give you an error on if it will give you an error. Okay, go, try that. Okay, welcome back. Let's see how that went. Let's go to the execute window and let's run that, or compile it rather. Now, here's where it complains. It complains line 27, which for us is in this window is this assert right here. Right, so right here, this is inside a const function, but you're calling the calls function here. And the compiler is just telling you, hey, you can't call calls inside here because it's not const. We've told it, because we don't have a const here, that something in here might modify lines. Even though it actually doesn't, the compiler doesn't look that far. It just says that we don't have a const function here. So we really need that const there to prevent these warnings from happening. So let's double check that this compiles to get back to working code. And then let's move to the next topic. Got 2 more topics in this module, so hang in there. If this is getting a little too much, there's a lot of concepts in this module. Maybe play with some of your own examples. Make yourself a small object and have it do a couple things to it, to some small data. Make it have an int and then play with it, just so you get used to having work delegated to the structure. Because we're going to take this concept and really add to it. We're going to go from here and we're going to add a lot more code. And all the code that we're going to add is going to be inside structures like grid. And we're going to make other structures like library and different kinds of solver structures. So everything we're doing from now on is going to be tucked inside these classes like this. So really make sure you understand this lecture and the way that you pack code and data into the object. So this is the second to last topic for this module, is going to be adding a name. Let's suppose the grid, you want to give it a name. Names are really useful for debugging mostly. And how do we give it a name? Well, let's talk about a couple ways. Let's go back to the source window here. How would we want to use the name? Well, here's one way to do it. Grid, we could have a thing called name inside grid. Let's say it's here. Let's say it's string name, okay? And I'll show you a couple different ways to do this. One way is to brute force it. You can actually say grid name equals, my grid. Okay. So that's how you set the name to a grid. And then inside the print function, let's make this a little better. We can say grid. Okay, do you see what I did there? So whenever you print the grid now, it's not just going to print out the size of it. It's going to print out what its name is. So that's kind of nice. So it makes the call a little more self-explanatory. If somebody just calls print, now it says, oh, I'm printing this grid. So let's run that and let's see what we get. There. So you see grid, my grid. What happens if you ran the same code but you didn't set the name? Let's say you ran that, right? So comment this out. So pretend this doesn't exist. What do you think this would do? That's sort of a mini challenge. Just think what that would do if you didn't set the name. And the answer is that strings, the string class, has a nice behavior where all the strings are initialized to empty strings. That's not the case with integers and built-in data types like bool, float. Those things are not initialized. You always have to initialize them. So if you had an int in here, like x, that's going to be random data. You'd have to set it to be 0 as an initializer. But since the string class itself has an initializer built into it, you don't need to do that for string. Generally, all the complex data types initialize themselves with a constructor, which is what we're going to get to next. But let's first do this. So first, let's just print what happens if you don't specify the name. Now we're giving it a grid, we're loading it, we're checking it, and then we're going to print it, but it has no name. Let's see what it prints. So go to the execute window and run this, and it just, as you could expect, it just prints nothing. So this is okay. But this isn't really great because you want to you kind of want to force people who make a grid, you want to have every grid have a name, right? So rather than having, I was going to say there's a second way to do this, which is to put a function in here. So you could have a function called set name, and that might set the name of the grid. And you could put the name of the grid in that argument. That's still not great because the person could forget to set the name. What you'd like to really do, and this is where we're going to introduce the idea of a constructor, is require when you make a grid from the very beginning that you give it a name. So anytime you make a grid, we're going to force the person who's making the grid to assign it a name. And then we're sure that the grids all get named. Now they may have, you could still give it an empty name, or you could still give it a name that conflicts with another name. We're not checking any of that, but at least we're requiring the person who's making a new grid to give it a name. And that's usually enough to prompt them to think, it's more like a communication mechanism. It's like saying, hey, don't forget to set the name of the grid. So rather than having a function called set name and then having a comment saying, don't forget to call this, instead what you do is you put the requirement up here. You say, when you build a grid, you need to give it a name. Now, where does this go? Because if you run this right now, let's compile this and I'll show you. It won't like this because we haven't told it. When you make a grid, it doesn't know what to do with this. It doesn't know this is a name. It doesn't know to assign this to the string name. You have to tell it that. So what it's telling you specifically here is on line 40, which is this line. You're trying to make a grid and it says no matching function call. You're asking it to make a grid where you're passing it a string. That's what this notation here means in the execute window. But you've got no function, no constructor function that supports that. So this is the concept of a constructor, and it's a really powerful concept that helps you create data objects that are well formed rather than formed by people forgetting to call certain things. So you make a constructor, which you actually call grid. You call it the name of the object. And now here, what we're going to do is we're going to have a name. We're going to pass in the name of the thing to the constructor. And again, there's two ways to do this. Let me start with the easy way you might understand is you might say, now name, we're going to say equals name. And now this is going to be a problem because it's going to get confused. You can't have the same word here mean two different things. One of them means the input to this function, and one of them means this name down here, right? This name down here is called name. So one way around that is to just call this like n, okay? This will work. We're going to get to a better version of it in a second, but let's compile this and make sure this works. So when you create a grid now, you're required to give it a name, and every time then the compiler will produce the code that will initialize the name field of that object. So let's go down here to the window and check that. So it compiles okay, and then we run it, and here, now it works. Okay. So make sure I'm not going too fast here and that you understand what we just did. We're creating a new function. It's just like any other function in the grid, except it's a special function that has the name of the data object. So this is the data object in C++, or the class name. And if we use that same name down here, it's a special thing called a constructor, and it's the way that you build one of these grids. And you can actually have multiple of these. Let me show you an example. You can have a grid with no arguments, and let's say the name will be something like untitled, okay? So now there's two ways to build a grid. You can call, here, let's have a little fun here. Let's call this grid 0 and grid 1. Okay, the first grid, we're going to initialize right? You see what I'm doing here? Let's look at this code. I'm making two grids. Oops. Oh, this is a sort of a syntactical problem. You actually can't, yeah, this is a glitch. You can't actually put parentheses. In this case, if I did that, it would think I'm trying to, it would think I'm trying to do a function call. So I'm going to make one grid with no arguments where I don't even have the parentheses. And then I'm going to have the second grid, grid 1, where I give it a name. And then let's print both these grids. Okay, so what do you think? So this is going to be a challenge. Let's go ahead and have you try this on your own. Type that code in and run it and see if you see if you can understand what will happen. And in fact, you can even try it with this, and you can see what error message would happen with the empty parentheses here. So go try that one right now. Okay, welcome back. We're close to the end here, so keep going. Let's see how this compiles. And you see that it gives an error, line 48, which is right here. It doesn't like the fact that I put these parentheses here, makes it think that I'm defining a function grid, and it's really not a function, it's just a grid. So I have to take those parentheses off. Unfortunately, that's a little hard to understand, but for now, just take that effect. So here we go. Let's compile that and run that. And now we have one grid that's untitled. So the first grid's untitled. Second grid is my grid. Okay, so that was just to show the idea of constructors and multiple constructors. The compiler will pick the right function. That's a general, the general case of that is called function overloading. You can have multiple functions like that. If you go to the code here, for any function, you can define it multiple times with different arguments, and you can just call it, and the compiler will match the function call to the function that has that number of arguments. So that's quite a powerful thing when you have functions that have the same meaning, the same action, but they take different parameters depending on how you want to call it. You can call them the same thing, and that can clean up your code. Makes the code seem a little more robust, because in both these cases we're trying to construct a grid object. We just want to construct it without a name or with a name. So having done that, let's just clean the code up a little bit. Let's get rid of this. Let's always require the name to be given, which is reasonable to do, and let's get rid of some of this extra stuff. So let's just have one grid. Let's go back and load it like this. Okay, so now we're back to something kind of clean. Let's make sure this compiles just to see we're on a steady ground. Now here's the last challenge for this lecture. I want you to add code to the print that actually prints the grid now. So rather than just saying how big the grid is, let's have the print function in the grid object actually print the contents of the grid. That'll be useful later as we start debugging. When the program starts to write in other words into that grid, it'll be useful to be able to print that out and see how it's doing and how what words are causing troubles or whatnot. So go ahead and make that code yourself. Write that code that inside the print. So inside here, add the code that's going to print out the entire grid. Okay, go. Okay, welcome back. Let's see how you did on that. We can work together to show one way of doing that. So here we go. We're going to go into the print function here, and I'll show you also a nice way to kind of clean up some of these prints. Like for instance, let's put the rows and columns into this same line. So we can say rows equals rows. Actually, we can even split this off a little bit. And cols equals cols. Here, you'll see what I'm doing in a second. So rows equals rows. Let's take out the line feed. And then let's put in a comma, cols equals cols. This is a little hard to read, but that's the way these print statements end up looking a lot of times. All right, let's see if I did this right. What I'm trying to do first, before I get to printing the entire grid out, is just to clean up the formatting so that the rows and columns shows up on the same line as the grid name. That'll just tighten up the print. So let's first see if that compiles. And it does, and then we get this. So that's sort of what I was after, just to make this look a little bit nicer. We'll play with different ways of doing that later. Let me add one more comment back on the source window. This is just strictly a formatting issue. The Google code style has 2 spaces for every line in. And if you have a continuation like this, a line continuation, because see, if we put this all in one line, it's going to overlap and get more than 80 characters. And some people like to code more than 80 characters, and they'll have a very large window, wide window. I've gotten used to the Google coding style where everything's 80 characters. So if you go more than that, you end up having to split your lines. And when you split a line like that, the indent that I'm used to is 4 spaces. Now you can do anything you want. You can you could make it flush. That's a little weird. People don't really do that. You could do 2, but sometimes it's nice if you're going to do 4. It offsets it from the next line of code, which might go in. But I just wanted to point out that's an arbitrary formatting convention, and you can kind of get used to something that looks right to you. Another way, some people don't like this because the 4 spaces doesn't line up with this 5, so they'll actually line this up, which is fine if you kind of are OCD about that vertical line. You might like that. I actually kind of don't like it because it's just depending. I mean, that depends on the fact that this is 4 letters and that's 1. So if this were something bigger, if this was going to be my output file, like what would you do then? Would you do this? I mean, maybe you do, but to me that's starting to look a little bit non-regular. So I actually, maybe it's just my eyes, but I get used to it looking like that. So to me that looks right, even though the arrows don't line up. All that formatting stuff is, people have lots of religious opinions, and you don't need to worry about it too much. For your own code, just do what you think looks right for yourself. Okay, but let's get to the main idea, which is to print the whole rest of the thing out, right? So we want to have a for loop. Remember, and you can see the previous lecture, the module 5, if you want to see how to do this. But let's do this as a loop. So we're going to say for string s in lines, do this stuff inside here, right? And each one we're going to just print out s with a line feed, right? So this will just print out the grid. And kind of a neat thing you can do is you can put like a little indent. So what did that do? This will print on every line a couple of letters first, and then it'll print the guts of the code, the guts of the grid, and then it'll print a line feed. So let's see how that works. And there we go. So we printed out this grid, which if you look at the original problem statement we're trying to model, matches nicely. So that's the wrap to this lecture. There's a ton more to do. We're trying to work towards having the program read a library, read a grid, find words in the library that fit the grid. And to do that, we've got a number of directions we can go. I think the next thing we'll do in the next module is to show how to read the grid from the file. Because if you look at this code, the part that looks a little weak is this load function. What we've done is we've coupled data with code. You've put this all this dog cat stuff, we've burned it into the C++ code itself. And that's not really a good code smell, is what they say. Like, it smells a little wrong to have that data burned in like that. So what we'd really rather do is read that dog and cat grid from a file, from a text file, which we make. Then we can compile the program once, and we can put different content into the grid by just changing that file and not recompiling every time. So file read is going to be the topic for the next lecture, and I hope to see you there.